Hi everyone, this is Zhensheng Li from SUNY Buffalo, and I'm very glad you opened this video, and I hope this online presentation will give a better experience. Okay, let's start. The topic of this presentation is about WaveSpy, that is remote and through screen attack by mmWave sensing. And the agenda of today's presentation will first, we will talk about the background and the motivation of this topic, and then I hope to show the rationale behind this new side channel attack, and then it's good to illustrate our system design and implementation with the performance evaluation. And lastly, I hope to discuss the future work and the limitation of this topic. Here, in the background, we know this is a very classic and still very hot topic that is about side channel attack towards the screen. So we call it screen attack for short. And especially in the IoT era, we try to deal everything through the screen of the electronic device, like the smartphone, smartwatch, and the laptop. This behavior will leave a huge security risk that can be utilized by attacker to steal our sensitivity information. And in the past 10 years, some researchers have proposed interesting mitigations, like they will focus on the compromising reflection of the user eye, finger movements on the screen, and also the electromagnetic leakage of the device. And especially last year, we know there's a paper about the acoustic emanation about the screen. And here we observed that these previous works mitigations actually are all based on isolation, which means no device approximation, no pre-installed firmware, and even non-light of sight. So here is a question, is the isolation truly secure against the side channel attack? We believe it is not, and we argue that there is still a risk, even the screen under the isolation. So back to this topic, if such side channel attack is identified, then we will say it will bring the limits of this topic and bring new research vision to the security community. And this is what we envisioned. Let's say we have a user named Bomber is typing his password to his computer in a room, and this room is isolated by a wall. At the same time, the attack Alice is trying to steal the password of the bomb remotely and through wall. However, to achieve this goal, the first question is how can we enable such new side channel? In our subphysical system security domain, we would like to first explore the mechanism of the target. And for here, for the screen, we find a very common mechanism among all the popular screens on the market, that is about the liquid crystal state. The screen content showing on the display actually are generated or controlled by the liquid crystal. Let's say we can see there is a deterministic relationship between the liquid crystal state and the screen content. So if the attacker can monitor in the screen liquid crystal state, then it will enable attacker to monitor this screen content. So this is our hypothesis. By using this LC-based side channel, we can conduct a new and stealthy side channel attack to remotely attack screen. So, however, to achieve this goal is not easy. There are mainly three technology challenges. First one is about information accuracy. We know that the launch pitch among the liquid crystal is usually around 0.2 to 0.3 millimeters. And in the mobile sensing technology, we cannot achieve such high level resolution. So how can we require the information of the liquid crystal is the first challenge. And then the next challenge will be, we know there are flash rate among the screen. So the internal time between each flash will be 4 to 10 millimeters. So how can we conduct an attack at so fast speed? That's the second challenge. The last challenge is about stealthiness. So to conduct such attack, we have to involve some mobile sensing technology. So how can we ensure that our attack is secretly and noticeably? To solve the first challenge, we introduce a concept called liquid crystal nonlinear effect. That is, when a continuous wave with the transmission signal that is projected towards the target, like the screen, or say the liquid crystal, it will produce or modulate with subcarrier frequency. And this subcarrier frequency is highly related with the property of the liquid crystal state. When this modulated signal radiates back from the screen, our received antenna will capture this liquid crystal state response. And then we can see that the liquid crystal response from the digital screen contains the rich information about the liquid crystal state and holds the potential to enable attacker to remotely capture the screen activities or the sensitivity information. Then the next question will how to estimate the sensing frequency, also the key towards the second challenge. So here we observe that the typical length icon among the screen is usually 3 milliseconds. So after calculation, we found the 24 GHz is the best solution for us in this application. And also 24 GHz has other advantages, like very good to handle the nonlinear response and also not restricted by the ISM. For the last challenge, we utilize the mmWave probe, which is very portable, lightweighted, ultra low cost, and small size. We did this probe in our Census 2018, and this probe is very easily can be disguised by clothes or hidden in a handbag. So we totally solved these mainstream technology challenges. And then to further prove our hypothesis, we did a preliminary test. First, we tested with 3 most common electronic devices. First is about data display, which is LED type and 24-inch size. And we tested with 5 very common activities on the screen, like online bank, Microsoft Word, and PDF reader. And the results are shown in this image. The x-axis is the frequency of the received response, and the y-axis is the amplitude of the signal. And we observe that the spectrum of the received response are quite different, and this difference also has a huge room for us to recognize the corresponding screen activities. And also we test on the Samsung smartphone, which is LCD type and only 5.8 inch with very common 5 activities, and the response are quite different, and similar conclusion can be get on the iPhone watch, which is OLED type, is only 1.6 inch. And besides these 3 tests, we also did something under the real world setting. We test with Microbox Pro with the 15 centimeters wall between mmWave probe and this electronic device, and we test with 4 very common activities, and we find the response are quite different. Besides this, we also want to know if this new side channel can work in our attack scenario previously mentioned. So here we test with on-screen keyboard. So one thing is here, each button plays the same role. So for the simple illustration, we just select the password as 1235, and the result are showing in the spectrum image, and we observe that the response of each button type is quite different. So by now, we have proved our hypothesis, but new problem appeared that we noticed that the difference of each button or the screen activities are not so significant. So to further such attack in the real-world setting or precisely identify the screen activities, we design our system WaveSpy, and this system mainly contains 4 modules: response analysis, screen activity recognition, and sensitivity information retrieval. I think are the more important modules, so I will emphasize on the last 3 modules here. And in the response analysis, we utilize a multi-level wavelet transform, and we find that the part 3 segment among the whole spectrum contains the real useful information about the liquid crystal, which is a 40-dimension feature vector. After we got this vector, we feed into the screen content type recognition modules, which is utilizing SVM with the Gaussian radiate-based function, and the data set will be n times m with n feature vectors and m devices, and the output will 3 candidates with the top 3 possibilities. And here we also, once we type the screen activities log in, we would like to use the spectrum function to augment the useful information, and then to use our sequential to credential model to reconstruct the sensitivity information. And here this model is based on DenseNet. And to better illustrate the performance, I prepared a demo.
This demo is to show WaveSpy, a new tool that sees computer and smartphone screens through walls. WaveSpy comprises a mmWave probe and machine learning model. WaveSpy can eavesdrop any screen and reconstruct the screen contents from meters to hundreds of meters away. Let's watch our demos. As the user switches from engine search to personal file to banking website on his computer, WaveSpy can accurately recognize the screen content. WaveSpy can silently detect on-screen keystroke on a tablet or smartphone as the user clicks on each button. WaveSpy can continuously locate a cursor screen position. As the user works on his personal device routine, WaveSpy updates the real-time cursor position accordingly. Thanks.
So here, this is more detailed information in this evaluation part to test if our system can work on the real-world setting. Here we totally include 6 different groups with different conditions of the screens, and also we tested with 100 different screen activities by our 10 volunteers. And there are 3 aspects about the evaluation. Firstly, about overall accuracy. We find that our screen activity recognition accuracy is more than 98%, and also in the display resolution evaluation test, we tested with multi of the screen resolution, and also the performance is very good, 99% accuracy. And also with different material, our system is still very robust, and the accuracy is around 99%. After we got a little sense about our attack performance, we also try to do something protect our users against this new side channel attack. And here we propose two kinds of countermeasures. First, we call it cost efficiency approach, which is mainly focused on hardware protection and user behavior protection. And second, we call it zero cost approach. It's mainly from the software protection. And in the last part discussion, I would like to emphasize 2 points. First is, although our attack system cannot achieve 100 accuracy, but this system will dramatically decrease the attack time complexity and the password entropy. And the second point is about feature work. In the next project, we hope to do 4 pixel-to-pixel remote image construction. And the takeaway message of the project is we propose a new side channel attack towards the screen that can enable attack to do something remote and through work. And the second is we suggest the sensitivity system should pay considerable attention for this attack. I'm very happy to answer your question. Thank you for your time.